dokie. So we want to check optimality using complementary slackness conditions. So this is one application of being able to use this duality and complementary slackness. So I ended up using a much smaller problem than what they had in the text reading. So we've got maximize 3x1 plus x2 subject to x1 minus x2 less than or equal to -1, negative x1 minus x2 less than or equal to -3, 2x1 plus x2 less than or equal to 7, and we've got x1, x2 are greater than or equal to 0. And what we'd like to do is check if x equal 1, 2 is optimal. Okay, so when xj is greater than 0, we need dual constraints, or constraint, the constraint that goes with that primal variable, tight. Okay, or in other words, we need to have an equality, and yi equals 0 for any slack constraint. Okay, well, let's see. Since we need to work with the dual constraints, let's go ahead and write the dual problem. Okay, so our dual problem, we look here for our, minimize those over those coefficients for the y1, y2, y3. So let me write down here dual minimize, and those were what? -1, -3, 7. So negative y1 minus 3y2 minus 7y3. So we'd like to minimize that. Then our first constraint, we have 1, -1, 2 on our y's and greater than or equal to 3. So that was 1, so y1 minus y2 plus y3, I think. No, plus 2y3 is greater than or equal to 3. And then this one, so we've got -1, -1, +1, and a 1. So negative y1 minus y2 plus y3 has to be greater than or equal to 1, and the y1, y2, y3 all need to be greater than or equal to 0. So there's our dual problem. Okay, so again, first, for any of the non-zero primal variables, we need the dual constraint to be tight. Okay, so both our variables are non-zero, 1 and 2. So both constraints, this went with the x1, this went with the x2. Those both need to be tight. So what that says is we need y1 minus y2 plus 2y3 to equal 3. And we need negative y1 minus y2 plus y3 to equal 1. Okay, so that's the first part. Okay, we got that. And yi equals 0 for any slack constraint. Oh, okay. Well, so for slack, we've got to go back to our 3 constraints here. And I need to plug in my 1, 2 into here. So I've got 1 minus 2. Okay, so let's come up here. Okay, so constraints, primal constraints. Okay, we have 1 minus 2. That equals I gotta look back here. Do I have the right dual? 3x1. Yeah. Okay. I'm just looking at something. I might have negative. Oh, wait. Yeah. Okay. I want to look here at that negative 1. So that equals negative 1 here, which is tight. No slack. Okay, then next constraint, minus x1 minus x2, so that's a negative 1 minus 2. Negative 1 minus 2, that equals negative 3. That was the right-hand side here, so that again is tight. No slack. Okay, so this was the y1, this is the y2. Now, does that mean they're non-zero? No, it just means they don't have to be 0. Okay, and then our y3 case, third constraint, 2x1 plus x2. So that's 2 times 1 plus 2 is equal to 4, but that is strictly less than 7, so there's slack. So that means, that implies that our y3 has to be 0. Okay, now going back to here, if y3 is 0, I have y1 minus y2. So y1 minus y2 equals 3, and then negative y1 minus y2 is equal to 1. There are 2 equations to unknowns. If I add those together, I get negative 2y2 is equal to 4. That says y2 would be negative 2. That's less than 0. Infeasible. Okay, so when we made sure that those 2 things were true, what happened was, because here's our dual, all those variables need to be greater than or that's a y3, need to be greater than or equal to 0. The dual is infeasible. Okay, so x equal 1, 2 is not optimal. All right. Well, okay, is, oops, x equal 2, 3 optimal? Okay, we go through the same sort of thing. Okay, we, again, we've got primal variables that are all greater than 0. So the dual constraints both need to be tight. We did that there. And so actually, I'll just write those again. Okay, so we need, okay, because they're the same dual constraints and they're still tight. So wish I could just pick that up and put it down here, but that's y1 minus y2 plus 2 y3 is equal to 3, and then minus y1 minus y2 plus y3 is equal to 1. Okay, I'm going to pause this for a moment. All right, so we need this, but then again we also need to check our primal constraints for the 2, 3, and looking back at those, we need to do 2 minus 3 minus 2 minus 3 and 2 times 2 plus 3, as we did down here. Okay, so our primal constraints. So yeah, the first one was x1 minus x2. So we've got 2, and that goes with y1. 2 minus 3, that's equal to -1. And so that one's tight. Then the next was negative y1 minus y2, so minus 2 minus 3, that's equal to -5, which is strictly less than -3, and so there's slack there. And so our y2 needs to equal 0. And then finally 2 times 2, and then plus our 3, that's equal to 7. Okay, so that one is also tight, which goes with y3. But so y2 up here actually is equal to 0. And so what we have are the equations y1 plus 2y3 is equal to 3, and minus y1 plus y3 is equal to 1. And so again, I add those, and I get 3y3. Yeah, okay. 3y3 is equal to 4, so y3 is equal to 4/3, and if y3 is equal to 4/3, that means y1 is equal to do I have that right? Something seems check my notes here. Okay, 2y. Yep. Okay, I think I got it. I think I had something wrong in some notes I have there. If y3 is 4/3, then y1 is, I think, 1/3, because you take 4/3 minus 1/3 right here, and you get 1. So 1/3. Okay, so those are my two non-zero values, plus y2 is equal to 0. So we can write that down. Y2 is equal to 0. And so those are certainly looking feasible, but we also need to check our constraints. And so for our dual problem, we had, remember that y1 minus y2 plus 2y3 needs to be greater than or equal to 3, and so forth. But okay, well, we already subbed those in, and we got, right, 1/3 minus 0 plus 2 times 4/3 is actually equal to 3. Right? So check. All right. And we're going to find the other one works as well, because, well, we had it up here, and those were the only two constraints. But, you know, you should check them. And so the other constraint was minus y1 minus y2 plus y3 is greater than or equal to 1. And actually, we know that it's equal to 1 because we had it right up there. But plugging those in, we get minus 1/3 minus 0 plus 4/3 is indeed equal to 1. So check. And so everything's feasible. Okay, so that means since our complementary slackness conditions we were able to hold and keep things feasible, then that means that x equal to 3 is optimal for the primal problem. Okay. And that is this idea of using complementary slackness conditions to check optimality.